The second example which we would like to consider is the case of Legendre polynomials. Well, probably you know that Legendre polynomials, probably you even encountered them before. Well, they're used in the solution of standard electrodynamics problems or in quantum mechanics. So these are very important special functions. So let's actually write down their standard integral representation for the Legendre polynomial. So here it is. So if you doubt, you may look it up in somewhere in Wikipedia, for example. So later, actually, we'll derive this integral representation using some more advanced techniques. So the phi is an azimuth angle in the spherical coordinates, and theta is a called polar angle. Okay, and we integrate over d phi. Right, and theta belongs to the segment from 0 to pi. Okay, we are interested in the estimate for large n. So in quantum mechanics, this limit corresponds again to a notorious semi-classical approximation. So let's try to compute an asymptotic estimate. So first thing that we notice is that this is not standard Laplace type integral. It has no exponential. Well, so what? Let's actually introduce the exponential with simple procedure. Like that. We rewrite the thing as exponential function with their corresponding log power. Okay. So now it has this exponential form. And actually our large parameter n, or lambda, when we used it before, now it's factored out. So clearly we already have our f function. So this is our function f of phi. And we will treat phi now as a complex variable. So let's draw the corresponding complex plane. Is our phi angle, and the integration segment is from 0 to pi. All right, let's find the corresponding saddle. So f of phi, the derivative is, okay, it's 1 over f, it's logarithm, so the derivative is 1 over f, times the derivative of this argument of the logarithm, which is simply I sine theta minus 1 times sine phi. And it's 0, right? So now phi is equal to pi n, actually. So, but here our integration segment stretches just from 0 to pi. So from all these zeros, we need to choose only two important points. Phi is equal to 0 and phi is equal to pi. Okay, and by the way, you see these are the edges of our integration segments. So, well, quite unusual. So the saddles of our integral expressions belong to the edges. Well, it will have some consequences, but let's actually discuss first the rest of their saddles. So obviously there is another saddle, for example, at point 2 pi, somewhere here, or minus pi to the left. And why do we have the right to discard them? Well, as you remember, the logic of saddle point approximation goes as follows. So you need to actually deform the initial contour so it can pass through their corresponding saddle. Let's imagine that we try to take into account contribution from this saddle. So there is some kind of steepest descent direction. I don't know, for example, this one. There are so-called allowed regions, the regions through which you can approach this direction. So you may imagine what's going to happen. So you start your contour here. OK, let's actually draw it with the dashed line. So you approach your saddle. Then you go through the saddle, and it gives you additional contribution from this 2π function. And then you have to return to your endpoint of your segment. And naturally, you will have to, you're bound to go through these forbidden regions of integration. Well, this is not good. That's why we will take into account just these two critical saddles at 0 and at π. So I erased this wrong path, and now we just need only these two saddles at 0 and π. Right. So let's compute the second derivative. OK, so, and actually we'll need the second derivative just at the saddles. So just keep this in mind. So we differentiated this thing once more. So 1 over f will give us 1 over f squared times f prime times minus I times sine theta and sine phi. Well, this thing is 0, right? Because sine phi is 0 and f prime is 0, so it's irrelevant. But there is additional term coming from the differentiation of the nominator of this expression. And this will give us cosine phi, the term proportional to cosine phi with negative sign. OK, sorry about the sign. It should be minus here. 1 over f I sine theta cosine phi. Well, that's better. Right, so we need the direction at 2 points, 0 and π. So let's compute the second derivatives at 0. So why do we need these kind of values? Because these second derivatives, they actually help us to find the steepest descent directions. Right, so f prime prime of 0 is simply, is 1 over f at 0, like that, times I times sine theta, and cosine of 0 is 1. What about f of 0? OK, f of 0, we plug in 0 here, so it's cosine theta plus I sine theta. So it's simple exponential, right? So here is our expression for the second derivative, which is quite nice looking, because now we see that the argument of our second derivative is the argument of I, which is π by 2, minus the argument of this exponential, so which is theta. So now we have this final expression, argument of f prime prime at the left saddle is simply π by 2 minus theta. Well, in complete analogy, we find the direction, the argument of the second derivative at the end point of our segment. So we simply plug in phi is equal to π into our f function, and we get cosine theta minus I sine theta. OK, so what we get, all right, and we plug it in here as well. So now we have minus I sine theta divided by f of 0, which is e to minus I theta. Right, so, and as a result, the argument of f of prime prime at π is equal to minus π by 2 plus theta. Right, so, and what else do we need? We need the conditions for our steepest descent path. As you remember, it's as follows. It's 2 phi. Let's actually denote this steepest descent angle as alpha. So 2 alpha plus the argument of f prime prime is equal to pi plus 2 pi n. Right, and here we go. So for the first point, phi is equal to 0. We have the following condition. So it's 2 alpha plus pi by 2 minus theta is equal to pi plus 2 pi n. So alpha is equal to, okay, let me think. Okay, actually, let me look it up. Right, it's better, so we'll just save time. So it's 3 pi by 4 minus theta plus theta over 2 plus pi n. So that's the steepest descent direction at 0 point at the beginning. And end point phi is equal to pi by 4. As far as minus theta over 2 plus pi n. Right, so let's actually draw this direction on our complex plane of this phi parameter. So the first is phi is equal to 0. So this is our direction. So theta is arbitrary. It changes from 0 to pi. Well, let's assume that, just for concreteness, that theta is somewhat small. So this direction is very close to 3 pi by 4 plus pi n. So 3 pi by 4 is this direction. It goes like that. But we add some small variation, theta over 2. All right, so it's something like, I don't know, like that. Or it's the opposite direction, like that. And the allowed regions are inclined by 45 degrees. So it's something like that, actually. So this is the first allowed region. And the second one is, well, symmetric. It's here. Right. And now the second direction, which is pi by 4. All right, and well, it's pi by 4 minus some small variation, minus theta over 2. Well, we assume for simplicity that theta is small. Right, so so pi by 4 is this direction. And then we subtract some small angle. So it's going to be something like that, actually. Or that, all right? And the allowed regions are inclined by 45 degrees, as before. So the first one. And the second one. Well, now, actually, I think you already guessed what the correct deformation of the contour is. So the most natural, actually, it's always the most natural path. So we start here, and actually, of course, we won't go like that. The more natural path is just we go like that, and then we connect to the second path, which is inclined in this direction. So this is basically pi by 4 direction, and this is minus pi by 4, right? So because the initial one 3 pi by 4. So here, for the correct direction, in the first case, we have to take n is equal to -1. So because it's 3 pi by 4 minus pi, so it's minus pi by 4. And for this for this direction, we make a choice n is equal to 0, because it's pi by 4 minus theta over 2. Right, and now we are ready to basically utilize our saddle point formula. And so just to make an illustration for you, here is our relief of our f function, and these allowed regions in the complex plane. So now we are ready to take into account both contributions of these two saddles. Well, the only subtlety, which you probably already noticed here, is that our saddle, each of these saddles is positioned at endpoints of our contour. That means, well, usually when we integrate along the saddle, what is happening? So first we need to go up to the saddle and then go down. So when the saddle is symmetric. So when we rise to this saddle, well, we accumulate the half of our integral, and then when we go down, we accumulate another half. Here, we don't actually climb to the saddle. We just here we are already at the saddle at the beginning of the contour, and then we just climb down along this steepest descent direction. And here we move somewhere along the lower regions of this relief of our real part of our f function, and then we climb up to the second saddle like that. So each of these saddles gives just half of the contribution which we usually write down. So we need to keep in mind this 1/2 factor. Okay, let me erase it. And let's continue. So first, let's compute the contribution from the first saddle. So En of cosine theta at from the vicinity of phi is equal to 0. Well, it's standard. As you remember, it's square root of 2 pi over lambda. Lambda is n in our case. So we need to plug in 1/2 and the modulus of f prime prime. So let me look up the correct modulus. Right, so f prime prime of 0, just to remind you, it was minus I theta sine of theta e to minus I theta. Right, so the modulus of this thing is equal to the modulus of sine theta. But since theta belongs to this segment, the sign is always positive, so no need for modulus sine. Right, so we add sine theta here. Now we need to compute the value of our f function at phi is equal to 0. Well, we actually did this before, right? So it was just a simple exponential. It was e to I theta, right? When we take a logarithm of it, we'll get just I theta. So here, it's just e to I and theta. Then there is a steepest descent direction, slope, which is for phi is equal to 0. It's this one, right? It's minus pi by 4. So it's okay. Let me check. Oh, sorry. It's it's minus pi by 4 plus theta over 2, of course. So it's minus. No. Oh, plus, yeah, plus theta over 2, right. And minus I pi by 4. So this is the contribution from this saddle, the left one. And in the same manner, we compute the contribution from their second saddle. So pi n, pi n of cosine theta at from the vicinity of pi. Again, it's 1/2 because we just raise to the saddle, right, climb to the saddle. So 2 pi over n as before, and yep, f prime prime at yeah. So it's the same f prime prime modulus. This saddle is the same. It's sine theta. And times they're almost identical exponential, but of course if phi is equal to pi, then we have -1 here, and instead of I n theta we'll get minus I n theta, and the rest is the slope of their steepest descent path, and the slope of the steepest descent path is right here. So n is equal to 0, so it's basically minus theta by 2 plus pi by 4. So minus theta. Oh, by the way, sorry, there is a plus sign here. So minus I theta by 2 and plus pi by 4, I pi by 4. Right. So in order to get the full contribution, we need to sum up the contribution from these two saddles. And as you can see, clearly see, they are complex conjugate and with common factor here. So the sum of them will simply give you the cosine, right? So let's actually write it down here. Pn of cosine theta Right, so 1/2 is going to be consumed by the cosine term, so it's simple. Oh, right, and there is 1/pi factor here. Actually, you know what? Let's write this pi here. Why not? So pi here and pi here. And now, OK, let me actually write down the answer. So when you combine these two contributions, what you'll get, you can change cosine to sine with simple trigonometric formulas. And in the end, we get a standard expression, which you can look it up in Wikipedia, for example. So this is this root. And then, well, I write this cosine in terms of sine. Right, sine as of n plus 1/2 theta plus pi by 4. So that's it. So this is an approximate, this is asymptotics for Legendre polynomials for large values of their number, for their index. So now probably you feel the power of this saddle point technique. So you start with just quite complicated integral representation, and just like that, you just in 10 minutes probably you already get the standard expression, which is used in scattering problems in quantum mechanics or in some boundary value problems in classical electrodynamics. So I hope you enjoyed it, and just let's move on. Все, Андрей.